Good morning and welcome back to computer graphics. And let's continue with our topic on textures. I just played back a few or rewound a few slides to just basically restart with the textures. So what are textures, or what's the problem textures are trying to solve? So one problem is that in computer graphics in general, that we specify everything per vertex. That's, well, not a problem specifically, but it's a feature of how we do computer graphics. Now, if you have a scene such as this one here with a wall and there's supposed to be some, well, pattern on the wall itself is obviously flat in this case here. So technically it's efficient from a geometric point of view to specify two triangles, if you want to stick with triangles for a second, specify two triangles and we get the wall done. However, if we want something on the wall, if we want some structure on the wall, if the structure is of nonlinear fashion, so it means it's not a smooth transition from one vertex to the other, then we're in trouble. Right? So we could specify some color here, some color at the top left, and some color top left and top right, but nothing in between, or no changes that are of nonlinear fashion in between. So the solution to that one is to apply a texture map to the object and just interpolate texture coordinates. What I stressed the last time already is that I don't want you to think of textures being stickers or being decals or being something that you put onto the surface just like a painting or so. The trouble with that one is that it will give you problems with more sophisticated texturing techniques. It'll work fine for just 2D textures, but for other techniques it'll give you trouble. So this is why I want you to memorize this definition here of textures. So I just want to give you a chance to look at that for a little while, so that it becomes absolutely clear what that's supposed to, what the texture is supposed to be. Okay. So, in difference to the previous sort of naive definition here, here we simply say a texture is a function, right? It's got some features. It's usually discrete, it's multidimensional, and it's got properties such as color. But in the end, a texture is nothing but a function. Okay, and a function, a mathematical function, can have pretty much any dimension. So keep that in mind. If we're dealing with sort of the 99% case where a texture is a two-dimensional function and it's being mapped onto a surface, right? This is what your texture would look like. Why do I say it's a function? I mean, this is an image, right? It's an image of a brick wall. So why do I claim this is a function? Well, what I want you to understand is that a two-dimensional image is really nothing but a discretely sampled function, right? For any point in x and y, or we generally call those coordinates u and v if we're in texture space, for any point uv, say this point here, we can look up in this image, we can look up a color, or for this point here we get a different color and here we get a different color. Okay, so effectively what this texture is, it's just a lookup table that maps a 2D coordinate to a, in this case, color value. Okay, so that's effectively a texture. If we have this notion in mind, then a 1D texture isn't a big deal. It's just one coordinate that is being mapped to a color. In this case, it's mapped to a gradient from yellow to red. So if I specify, let's say this is normalized. If I specify 0, I get yellow. If I specify 0.5, I get orange. And for the coordinate 1, I get red. So with this notion in mind, 1D texture is just fine. I mean, it's a one-dimensional function, right? And the same is true for a three-dimensional function. So here, that's a scan of a human body. It's a three-dimensional data set. And again, every point in this three-dimensional space, let's again assume it's normalized between 0 and 1. So we can select x, y, and z's depth in this case, and we get a sample value. Again, we would probably not call them x, y, z, but u, v, w, but that's not the point, right? It's just three-dimensional coordinates that are mapped to a color. And this can happen via a discrete approach, so with a lookup table with an array of more technical terms. Or this could literally be a function, right? You could say, if you want to use a one-dimensional texture, you could literally say that's a sine, okay? Sine in terms of sine, cosine, right? So you could say, okay, well, I put in an x, say between, again, 0 and 1, and I compute sine of x, and that's the result. Okay, that's a number. Or x squared, or x to the third power, or 5x times 10x squared minus 6. Yeah, it's still a function, and that can be used as a texture. The key point here is that these functions don't have to be linear, right? I mean, I used sine, I used a parabola, or whatever function. And here, when I use a lookup table, again, that can be basically an arbitrary function. And that's the key observation here, really, that we use a non-linearity on top of the linear interpolation of a triangle. Okay, so how does this work? How do we apply these 1, 3D, 2D, whatever D textures, really? So the idea is that instead of interpolating the values that we see on the object directly, we interpolate an auxiliary data structure that's called texture coordinates, and then use that to map the texture to the object. So here's a very simple example. Say we have a quadrilateral, and I set, again, everything is set per vertex. So per vertex, I specify, in this case, 4 2D texture coordinates, okay? And they range between 1/4 and 1/4 to 3/4, 3/4. 2D texture coordinates, so I have 2 parameters per vertex, okay? And now I can basically look up these coordinates inside my texture space. And I said that the texture space is usually normalized between 0 and 1. So 0, 0 is here, 1, 1 is here. So where's 0.5, 0.5, 1/4, 1/4, it ends up being here. Okay, 3/4, 3/4 is here. And then the other 2 coordinates as well. And now what happens is that I look up for each point inside my polygon, in this case quadrilateral. I can interpolate these coordinates to get coordinates inside the quadrilateral or inside the triangle, whatever I want to use, okay? And that's a smooth interpolation. And then for each point, I take those interpolated coordinates, look them up here in texture space, and then apply the result that I get from the texture, in this case a grayscale value. I apply that to my object. Why is that different from this idea of, well, sticking the decal onto the surface? I mean, I just literally stick the face of Lena here onto that surface. So what's the point? Well, the point is that if we use different textures, say 3-dimensional textures, this still works. My idea still works, whereas the stick the decal onto the surface idea fails, right? I mean, how do I stick a cube onto a quadrilateral or triangle, right? It just doesn't work. However, if I just say, well, these vertices here have now 3-dimensional coordinates, and these 3-dimensional coordinates sit somewhere in this cube, then I can interpolate this just fine. Yeah, so I specify 3 coordinates here, 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 and here, and then I can basically interpolate the 3D coordinates inside the object and get a 3-dimensional coordinate for every point inside my quadrilateral. And that, again, I can look up in my discretely sampled or in my analytically given texture. And then this corresponds to a cross section through the volume. Right? But it just works fine. And the same is with the 1D texture. So I just specify 1 coordinate for each vertex and then interpolate this 1 coordinate and look it up in the 1D texture. Okay, so it's not really a complicated thing. It's actually pretty simple, but it's different from this notion of just sticking something on the surface. There's another advantage over this simple notion, that is, we can do a lot of things when we have this just functional concept. Okay, so we can apply a lot of other things to it. Let's first look at the discrete sample texture, and let's look at a few basically names that I'm going to use in a second. So first of all, I said texture coordinates are usually called UVWs. The reason is we don't call them XY or XYZ. The reason is to distinguish texture coordinates from spatial coordinates. So it really doesn't matter how we call them what names we give them, but the general convention is to call them u, v, and w's. And often you hear people talk about UVs, which means they want to talk about texture coordinates. So there's sometimes the variable names become the actual term. So as I said a couple of times before, generally texture coordinates are normalized between 0 and 1. So there are a few exceptions where we use other types of coordinates, but normally they're always normalized between 0 and 1. The advantage of this normalization is that our texture, if it's discretely sampled, of course, does have some size, right? Our 2D array, 3D array, 1D array, it's got some size in U and in V and maybe in W. And if we increase that size, say we would want this texture here to be of higher resolution, not just 64 by 64, but maybe let's say 128 by 128, right? Then we don't have to adjust our texture coordinates to the texture resolution if we just keep them between 0 and 1. And to get from the texture coordinates to the actual pixel coordinates, or texel coordinates to be more precise, so that's how we call a single pixel in texture. We call this texture element. It's pretty straightforward. We just use the coordinate and multiply it with the size, and then chop off the decimals, and then we know where we are, right? So then 0 is still mapped to 0, and then whether the top right corner is then should be in this case mapped to 63 by 63. So we might want to multiply it with 64 minus 1, but those are the details. Okay, so the texture coordinates are normalized and they map onto something that is basically a set of array elements that we call texel. Now with that basic idea, we can turn something on the left to something on the right. So we can basically add, well, non-linear behavior to the surface or textures, which is kind of the same idea. Where can they come from? They can come from just any acquisition process that creates a discretely sampled representation. So for instance, photos or simulation or video. The pro of that is it's trivial, right? I mean, images is something that we know what a JPEG is or PNG or so, and those are all regular grids, maybe compressed in some way or another, but the bottom line is they're all regular grids. They're all 2D arrays, and then if we use other acquisition processes, for instance simulation or some three-dimensional acquisition processes, we also can get three-dimensional arrays, three-dimensional textures. Trouble is they're obviously they consume a lot of memory, right? So if you download a game or if you buy a game as a Blu-ray or so these days, you'll notice that they are gigantic in size, right? So they're in the sometimes hundreds of gigabytes. And one reason for that is that you have these tons of high resolution textures. So they consume a lot of memory, and that might not only cause a problem when you want to download your game or when you want to install it on your device, but also during runtime. So this data needs to be kept in memory. So you also need a lot of storage for that one. And since you capture them once, they are also fixed. And in particular, if you capture a photograph of reality, it happens to include lighting, right? And that's sort of a pretty obvious thing, right? If I take a picture, it's obviously lit, otherwise it would be black. And that might not be a good idea because it was captured under certain lighting conditions. So I had a light source somewhere, and that would cause certain reflections, refractions, shadows, all of that stuff. And that's all in that image already. That might be an advantage because I don't have to simulate it anymore. But what if I want to change the light source? What if I want to change the light source's position? Then I have to somehow undo that, which is not impossible, but it needs to be done. On the other hand, a texture doesn't always have to be this discretely sampled thing from an array. It can literally be a function, right? Sine u times cosine y or so, okay, would create a wavy pattern. The advantage of that one is it's got unlimited resolution, assuming that I can evaluate my function at an arbitrary resolution, and I can throw in whatever algorithm I want. But the downside is it requires programming, right? So you might say, why is programming a downside? Well, if you're not a programmer, then taking a photograph is somewhat easier than writing code. Okay, so there's obviously a downside to it, and then it might not be trivial to get certain things done. Okay, so here is an example of a scene that uses various different sources of textures. So on that sphere, you see a photograph of a parrot. And now write an algorithm that generates an infinitely sized or infinite precision version of a parrot's face, right? So that's obviously going to be a big deal, whereas taking a photograph is pretty trivial. On the other hand, getting a checkerboard pattern is very simple from an algorithmic point of view, right? You would just basically take, multiply the coordinates with some value and then make odds black and or transparent in this case, and even white. Right? So that's a very simple algorithm. Also, the cloudy structure that's underneath the checkerboard pattern is also something that was generated algorithmically, and that's also not a big deal. Okay, so some things work better one way and some things work better the other way. But a texture, again, is just a function and we can use it any way we want. Okay, now that we've got a little bit of an idea how we can design a texture or how we can store it, what it is, how do we get it onto the surface? Well, we get it onto the surface by the means of something that's called mapping. Now you might ask yourself the question, like, what's the point? Didn't he just say, well, we specify these texture coordinates and they get interpolated and it's all fine? Well, yes. The trouble is just how do we get these texture coordinates, right? How do we, we have to design the geometry of an object, scan it, build it with some tool or whatever, and set it up. And it doesn't come with texture coordinates automatically. Right, so we have to specify these somehow in some smart way. For a flat region, for a quadrilateral, that might be a very straightforward process, but for another object, it's not that straightforward. Okay, so let's look into the details a little bit how we can do this. So, what's a mapping? Mapping is a transformation, and in this particular case, it's a mapping from a surface point to its texture value. Right, so it's just a coordinate that we set, and that coordinate coincides with a vertex, right? A vertex might have a texture coordinate, and that coordinate says, okay, how do we transform that point into texture space, and then ultimately look up the value. Okay, so, and what this ends up being as a whole, since the texture itself is also a function, is a double function application. Okay, so we have the 3D coordinates of the point itself, of the vertex, and that has texture coordinates, let's call them UV here, and those we need to specify, and then those UVs get then turned into, well, usually a color value, but again there's situations where this is not the case, but let's stick with a simple case here for a second, into a color value. So ultimately we want to map a surface point that has XYZ coordinate to its color. That's what we always need to do. So from a graphical point of view, this is what this will look like. So here we have a table, geometry of a table made up of a ton of different vertices. And we have our texture, which is this marble-like thing here. And we want this whole table to, well, be covered in marble, right? For the top, that seems pretty trivial, but what do we do here in the areas that are bent in this spherical shape here at the bottom and then around the table's boundaries. So how should we do that? Well, let's again first look at the basics here. We have a XYZ point. That XYZ point has texture coordinates, and that's the thing we're trying to achieve. We're trying to find texture coordinates, and then that is looked up in the texture, and then we get the color. Okay, so question is again, how do we get this thing done? How do we find for each vertex a proper texture coordinates? Well, it boils down to finding a surface parametrization. Okay, so if your texture coordinates are, say, two-dimensional, because we don't want to use a two-dimensional texture, you need to find a two-dimensional parametrization of your three-dimensional point. If you're using three-dimensional texture, you want to find a three-dimensional parametrization of a three-dimensional point, which sounds a little bit easier, right? So if it's the same thing, probably all you have to do is normalize your coordinates. But for 2D coordinates or 1D coordinates, that's actually a non-trivial process. Okay? If we're talking about a watertight surface, well, it's a two-dimensional manifold, right? It's in 3D, every point has 3D coordinates, but it's a two-dimensional thing. So there should be some way that we can find a parameterization of that surface. Well, it turns out it's not that trivial. Take just a very simple example, a sphere, okay? Take a sphere. Now, map a quadrilateral to a sphere. Right? That's what we're effectively doing. Right? If we want to parameterize in UV space, then it's in planar space, and we want to map that plane to a sphere. Okay, and now you can just imagine the practical implication of that. I want to take a piece of paper and fold that around a sphere. It'll start to crinkle. Why? Because we'll have distortion in that way we try to fold that piece of paper around the surface, right? Or it'll overlap, which is even worse. So we would get multiple texture coordinates on one surface. So it's not that trivial and potentially not distortion free. So some areas will have to be stretched and some area will have to be squeezed. And in a situation of something as simple as a sphere, you actually get infinite distortion at the poles, for instance, right? Something needs to be squeezed infinitely much. So long story short, it's something we need to think about. So what's the structure? What's the underlying structure? Okay. Again, we have vertices. Vertices have coordinates. They might have colors. They might have normals. I talked about this before. And now we'll give them additional texture coordinates. And then if we, for instance, use a shared vertex list, we have this additional triangle list where we say, okay, well, the first triangle is made up of vertex 0, 1, and 2, and then we could look up the data here. So that's, I guess, all very straightforward. Then we look up the texture coordinates for the vertices. In this case, we have a polygon here, not just well, it's a four-sided, four-vertex polygon. It's not just a quadrilateral, or it's not just a triangle. So this works for pretty much any polygon or any object, right? We'll just map those coordinates onto the vertices and then get the textured object. Now, how do we solve this parameterization problem? And it turns out that's a very complicated thing, up to the point where it's impossible to achieve. So the general approach to this is start with something that is not trivial, but it's also not super hard, and then try to take your object in question that you want to texture and find a mapping from your object to this sort of intermediate structure, and then use what you know how to parameterize this intermediate structure. Let me give you an example. If you have a cylindrical object, such as a soda can here, the soda can isn't flat, so it's not trivial, but it's not super complicated either to find a two-dimensional parameterization. As a matter of fact, I've already mentioned this two-dimensional parameterization a few lectures earlier when I talked about geometric models, more specifically geometric models 2. How can I parameterize a cylinder? Well, one parameter, if I want to parameterize it in 2 dimensions, one parameter is simply height. So v could simply be the y coordinate, maybe normalized between 0 and 1, but that's pretty much it. And then the other parameter, u, is simply phi. It's simply the angle, the circular angle. And if we specify this as arc length, we simply divide it by 2 pi, so that again it's normalized between 0 and 1. Okay, and with that we can, for each point, each xyz point, we just need to figure out its y and its phi, and we have the coordinates. Okay, for the unit sphere, I've also mentioned that in geometric models too. There's also a way to parameterize this using 2 parameters. Okay, in this case it would be phi and theta. Okay, so I end up with 2 angles, and these 2 angles describe every point on the surface. Okay, so I either would have to convert xyz's back to the angles, or, well, I somehow constructed the xyz's and I simply can remember those 2 angles and use those as texture coordinates. Now, didn't I say it's hard to map something onto a sphere, that we get distortions? And why is this suddenly, I mean, straightforward? It's sort of in the construction. Well, it's a straightforward parameterization, or it's a parameterization, but it's not distortion free. Okay, so if we take a texture here, for instance, in an image of our planet, and we want to map that to the surface, then, well, let's see what happens. A lot of this area here at the bottom, like all this white area at the bottom or top, ends up being mapped onto a very small part of the sphere, namely just the polar regions, right? Because everything kind of falls together at the poles. What I did here in this texture, I compensated for that already. So I've basically stretched out the polar regions to a very large region in the texture, so that when they get mapped later on and they get distorted, shrunk together, that in summary, it looks correct. It looks like Earth is looking from space. Okay. Now you might say, well, wait a second. I know this picture here, right? I know this picture. That's simply a map of our planet. Well, yes, because when maps are generated, you need to solve the very same problem. Well, technically the inverse, right? You have to map from a sphere back to a plane to look at these things. But as you should know, this is not distortion free, right? So Canada isn't that gigantic country. I mean, it's the second largest country in the world, but it's still not that big as it appears here, or Alaska, because it's also stretched out, right? Same is true for Greenland, Iceland. So everything towards away from the equator towards the poles needs to be stretched out so that it fits onto the surface. Okay, so while it's possible to do these parameterizations, they're not free of distortions. Okay, and here are kind of the mathematical details. What you would have to do is, if you want to invert the function at the top, right? It basically just involves inverse, sine, and cosine, and then you can combine them to the tangent, and there's this Arcos tangent 2 function that is defined this way here, which is something that computer scientists like to use, which basically just kind of combining both hemispheres. But it's possible to invert simply x, y, z's, and then you need to know the radius, of course, as well, to get back to the original surface parameterization. Now, what does that have to do with my initial idea of take something that is your thing in question? I mean, we don't always want to use cans or spheres, right? We want to have, I don't know, arbitrary other object, bunnies, horses, humans, whatever that we want to texture. As I said before, you generally use a proxy, and this proxy could be a cylinder or a sphere or a box. So what you do is you take your object and then you put your proxy object, say a sphere, where you have a clue how to set up texture coordinates around your original object. Okay. And then you figure out, okay, what point on the sphere should I map onto the surface? And then you check, okay, that point on a sphere, what texture coordinates does it have? And that's what I assign to the surface. So the process is basically a two-step process. You first figure out the texture coordinates of your proxy structure, for instance, this way, put that around your object, and then figure out how can I connect my object to that proxy structure. And the connection could be the closest point or the point along the normal, right? So you take your surface, you construct the normal, you extend this normal outward and check where it intersects with a sphere, a box, or a cylinder, or some other object. So there's other proxies, but sphere, cylinders, and boxes are probably the 3 most popular ways. Okay. So once you've found that, you simply just need to use your texture. So again, let's just show that as a whole here. So step 2 is, once we found that mapping, how do we use it? Okay, and let's say we want to do ray tracing, we want to ray trace an object. Okay, so the first thing we do when we ray trace, or the thing that we do when we ray trace, we find intersections of objects with rays. Okay, so we find our ray object intersection. What do we get out of a ray object intersection? Well, we get the intersection point, and this is generally given as, say, for triangle barycentric coordinates and a distance. Now, we already know that we can use those barycentric coordinates, for instance, in a triangle, to interpolate all the values of the triangle. And the same is true for other objects. You generally get out of the intersection, you get a set of interpolation parameters. And we use that now to interpolate our texture coordinates. We look up in the texture, we look up the point, ST or UV, and then we get back a color, for instance, and that color we use to color the object. Okay, and just as a quick reminder here, that's barycentric interpolation, in case you can't remember that despite the fact that I've repeated it numerous times. Okay, so those are just ways how to define weights inside an object. And we've used barycentric interpolation inside triangles and bilinear interpolation inside quadrilaterals, and there's other interpolation means for other objects as well. Now there's this issue that your coordinate that you look up doesn't necessarily have to hit a sample point. Okay, what is that supposed to mean? Well, if you have a texture, say 100 by 100 texels, and I look up a point that's say 0.51 or so. So that's, if I multiply this with my texture resolution, I might not end up exactly at a sample point. Let's call it 0.511. Okay, then it's kind of 10% off my 51st sample point. So what do? Well, as I said, you can simply truncate. You could simply say, okay, well, I just want integer coordinates, so I truncate, or I round my texture coordinate. But that would basically create a very blocky appearance. So for instance, if you zoom in closely, then a lot of points on screen would get mapped to the same texture coordinates because they differ slightly in texture coordinate. When you chop off the decimals after multiplying them with the texture size, they would all get mapped to the same texture coordinates, hence they would all get mapped to the same value. So this would mean a lot of pixels on screen would get the same texture value, they would look the same, and that creates a blocky appearance. Sometimes that's something that you want, but usually you want things to smooth out if you zoom in. So what do you do if a sample point ends up in between texture values, which is, I guess, the usual case, that a sample point happens to be exactly at a texture element is very, very unlikely. So how do we do this? Well, what would be better is if we could take all adjacent texels into account and use them to figure out the value of the texture in between. How do we do this? Well, how do we figure out things in between values? We interpolate. And what did I tell you about interpolation inside regular grids? Well, I told you that there's this thing called bilinear interpolation. Well, that's a repetition. It's not really today, but it's the same topic. It was in the last stream that I gave you this idea of interpolating bilinearly inside a quadrilateral or rectangle. And that is used, for instance, to figure out a point in between textual values. Okay, so what does this look? Here's the difference between the two approaches that I just mentioned. So here we have this what's called nearest neighbor interpolation. So we simply round or truncate the texture coordinates. Then a lot of values would get mapped to the same texture value, and then only if they differ significantly in texture coordinates, we would get a different value. So here I used the same texture, but I interpolated the color bilinearly from the texture coordinates. And this way, if I zoom in, I get this sort of smooth transition between values. Which one's better? Well, as I said, it depends. In many scenarios, you want this situation here, that things get blurry instead of blocky or pixely or whatever you want to call this. Right? But there might also situations where this one is beneficial. For instance, if you want to render a checkerboard pattern, right? That wouldn't be a good idea. Okay, so here's another example. And what other pictures could we use other than CAD images? I mean, after all, this is on the internet. So here I used the texture and I zoomed in and I used this nearest neighbor interpolation to give you a better idea of what I'm currently doing. Okay, so I now map this fairly low resolution texture to a relatively large patch, and I assigned as texture coordinates simply 0, 0 to 1, 1 here. Okay, and I did this just for the fun of it. I started at the top left and ended up at the bottom right. So I kind of flipped the y-axis, which is something that you often do because images are often parameterized just by pixel coordinates, and then you would start from the top left and then you would go down to the bottom right. So when we index arrays, they are often flipped in y direction. So if you're doing computer graphics programming, don't be surprised if your textures are always upside down. This is because in pixel you count, in arrays you count, right, from top to bottom, whereas in coordinates you would always do this from bottom to top. So nonetheless, so those are, if I specify these texture coordinates, I get, well, my low resolution kitty image here, or kitten image on a patch. Okay, great. Now, I said texture coordinates are normalized between 0 and 1, but what happens if I don't follow that idea? Okay, I mean, after all, those are just things that I specify as vertex parameters, and they are in floating point. Okay, so what happens if I'm just nasty and I just happen to set the texture coordinates of this vertex here, texture coordinates here, at least I hope, yeah, looks fine. So again, what happens if I specify these out of range texture coordinates? So, well, we could throw an exception or crash, or we can simply use that and say, well, okay, let's somehow deal with that. And that's what's called wrapping, how to deal with these sort of out of range texture coordinates. And there's different ways to deal with those. And the first one is what's called clamp to border. So you basically specify a border color that can be anything. And in this case, I've chosen white. So then any texture coordinate that's out of the range 0 and 1, and it doesn't matter if there's just x or u or v out of range. So if one of the two is out of range, we simply use our border color, and that's what we get. So in this case, we, well, get a thick border around this kitty. So another possibility is what's called clamp to edge. And that's just a parameter you set when you enable a texture. When you use the texture, you say either clamp to border or clamp to edge. What happens in clamp to edge, that means any coordinates that are outside the range 0 or 1 are simply set to either 0 or 1. So you basically do a maximum of texture coordinate in 1 and a minimum of texture coordinates in 0. Sorry, the other way around. Minimum of texture coordinates in 1 and maximum of 0 in texture coordinate. This way, a texture coordinate bigger than 1 gets mapped to 1, and a texture coordinate smaller than 0, well, gets mapped to 0. Okay, welcome folks. We're talking about texture coordinates here. So, and what this will result in is this awkward smear thing. Again, compare that to the clamp to border approach. Which is better? Again, it totally depends what you intend to do. So what else could we do? We could say, well, okay, if our texture coordinates are too big, so we basically leave the range on one side, let's re-enter. Let's use sort of cyclical or spherical texture coordinates, okay? And this is what's called repeat. In this case, we simply take, from a mathematical point of view, we simply take the decimal part of the texture coordinates, right? We don't care if it's 1.5 or 0.5 or 10.5. We just use the 0.5 from texture coordinates, and this will lead, well, to a repetitive pattern that we're using. And here again, you see this beauty of just thinking about textures as a function, okay? So how do we get this repetitive pattern? Well, it's easy. Just take the truncate the texture coordinates and take the decimal part, right? And you're done. Well, this again, which is better? Which one's better? Repeat, clamp to border, clamp to edge. Depends on the situation. So this is why this is a parameter to choose. And there's a ton more. So I just want to give you one more, and that's mirrored repeats. In this case, you would just invert the texture coordinates between 0 and 1, whether they're odd, whether the part in front of the colons, like the whole part of the number, is odd or even. What this leads to is that you get texture coordinates here between 0 and 1, and then here from 1 to 2, we basically traverse the texture in an inverse way. Okay, so this here 0 and 1, and then 1 down to 0. What's the effect? Well, first of all, it looks kind of awkward with kitties, but the advantage is it's obviously continuous, right? Because the transition from the inside and the outside region is the same texture coordinate, hence it's the same value in the texture, so it's the same color. And again, there's situations where one makes sense and where the other one doesn't make so much sense. You can also, of course, if you have a situation such as this one here, you can just generate your image in a way that the left and the right looks the same. Then repeating texture coordinates works fine and creates a continuous appearance. If you remember the brick wall texture that I had a few slides ago, that was such a texture that it's repetitive in nature, so that the left and the right look exactly the same, and then it works fine with repeat. So here's another example of that situation, and I just want you to look at this for a second. So first of all, there's two things that I want to show here. First, I can choose these clamp to edge, clamp to border, repeat, mirrored repeat. I can choose this separately for each direction, right? I could choose for UVs, for two-dimensional texture coordinates, I could say, okay, clamp both, clamp to edge in this case here, or I could just use clamp in one direction and repeat in the other one, okay? So, that's one thing. The other thing that I want you to look at, I want you to look very closely at that image here, okay? And the input texture, so the texture coordinates are from 0, 0 to 3, 3 in this case here, okay? So, that means we get valid coordinates from 0 to 1, and then sort of out of range coordinates, they're not invalid, but they're out of range, to 1 to 2, and then 2 to 3, okay? So this is how this quadrilateral here is textured. Now, the other obvious thing is the texture that I'm using is a checkerboard with red and white texels in it, okay? So far, so good. So what I want you, what I challenge you to do is tell me what's the resolution of the texture that I'm using, okay? Let's assume there's just alternating red and white texels in the texture of, right? Okay, otherwise you can't compute the resolution. But what's the resolution of the texture? I mean, you might want to look closely at that image here. And again, I'll get out of the way. What is, if you look at that image or any of the other three, what's the resolution of the texture that I'm using here? Okay, and again, it's just red and white texels alternating. So it's not 10 red, 10 whites. It's just one white, one red, one white, one red. So what's the resolution? Can anyone tell me? It's got to be something by something. Let's just count. Okay, so we got 7 by 7 here. Sounds like a good idea. Alternative answers? At least someone's still listening. That's good. So we got a 24 by 24. Okay. Anything else? 8 by 8. Okay. Anything else? Let's see. What other numbers can we produce? Okay, so while the rest is still thinking or not, let's solve this thing. Okay, let's look at this image here specifically. Let's see how you came up with those numbers. Let's make a guess. Okay, let's start to count. Okay, so we've got a white texel here, so that's 1. We got a red one. We got a white one. We got a red one, white one, red one, white one, and we're at 7 now. But then again, and that's what most people think. So actually, most students that I ask, they tell me 7 by 7. Okay, which is perfectly fine because you see 7 by 7 grid. But as you pointed out, no, there's one more. There's a red one. So, but I only see a 7 by 7 grid. Well, you see an 8 by 8 grid, but you see the last texel being extended. Let me try to do this here. So if I block this with my fingers, okay. Then you can better see how big the texture is. Okay, I'll try to hold still here. Okay, so you get it? So it's 8 by 8, and the last one is smeared out. So this is an 8 by 8 texture. Okay, that gets, in this case here, repeated 3 times, and you see that this is a pattern where the left side fits the right side. As a matter of fact, it's actually opposite, but it fits nicely. It feels nicely spaced. So it's an 8 by 8 texture. But it's often interpreted as a 7 by 7 because that's where your vision starts to break down. So it's a vision problem. Okay, so this is a wrapping, and this sort of wrapping and sampling are two things that we need to specify, right? We need to specify, do we want nearest neighbor, do we want linear sampling, and there's other sampling modes as well. I'll talk about those later. And there's this concept of wrapping, and that comes on top of the texture coordinates that you specify for your objects. Okay, so those are parameters for a texture. What does this allow you to do? Well, it allows you to do, well, high frequency color variations, in particular non-linear variations across surfaces, and they're independent of the surface resolution. Right? That's a nice thing. So we can still specify a quadrilateral here, but we get an image on the surface. So that saves space. I mentioned that these textures can consume a lot of memory, but still they just consume, well, one color value per point if we're talking about RGBs here. Whereas if I were to triangulate that, I would need tons of vertices, and each of those vertices would require, well, 3 floating point coordinates. So that would be a significantly larger amount of data, and that would have to be pushed through the entire pipeline. Okay, so textures are kind of a nice idea to increase this, well, literally the texture, now the English term, the appearance of an object. So here's again a scene from a game engine. Now, when I apply textures to a scene, well, I can get this to, well, look more realistic. I can mimic material properties such as stone or iron or whatever, rust. What I want to do if I choose those textures carefully. But what else can we do to increase the realism? Well, it takes light interaction. We don't want to just throw the textures in an unlit fashion onto the surface. We want to add lighting. Okay, we want to add light and compute lighting and sort of shadows along with it. So how do we compute lighting, and what does that have to do with shading, which is kind of the topic of this particular stream, right? Texturing and shading. Remember when I said we have Phong lighting? Phong lighting was this idea of using a diffuse, a specular, and an ambient term and adding the 3 together. I already mentioned that this guy Phong invented another concept, and that is called Phong shading. Okay, it's not the same as Phong lighting. Okay, so what is Phong shading now, and what is it compared to what else? So here's the thing. Again, when we have an object, in this case a triangle, and we want to fill it, we want to shade it. Okay, we interpolate things from the vertices. I mean, you should have, if there's one thing you should have figured out by now from my streams, is that we interpolate a ton of things. Interpolation is a very prominent concept in computer graphics. Okay, so, and what can we interpolate? Texture coordinates. We've just seen how to interpolate those. Positions, or colors, or normals, which is something that we need for lighting. If you don't know what lighting and normals have to do, just step back, take a look at my previous streams, and there I explained how lighting works, how Phong lighting works. But for now, if you haven't followed those streams, it's sufficient to know that the normal, which is a vector that is perpendicular to the surface, is important for lighting. Okay, it's important to computer graphics light. Now, as I also mentioned a ton of times, is properties are specified per vertex, and that includes the orientation, that includes the normal. Now we can do 2 things to compute the lighting inside an object. One is we could compute the light at the vertices, right? We take the normals that are given, we take all the other parameters such as viewing direction, light direction, and for instance compute Phong lighting. Okay, Phong lighting was just this one formula that takes normal, viewing direction, light direction, and a bunch of material parameters and computes the color out of that. Okay, so we can compute 3 colors for the 3 vertices, and then interpolate those colors into this object as if they were, well, just regular colors, as if they were specified right away. This approach is called Gouraud shading. Okay, so this approach is called Gouraud shading. It's just, it computes the colors per vertex and then interpolates them across the object. It's also sometimes called vertex lighting. Okay, which is really nasty because it's a shading technique, but it's called vertex lighting. Why? Because we compute for this particular shading the light per vertex and then interpolate it. Okay. So the second approach, and again that is also an invention by Bui-Tui Fong, is that we, instead of computing the light per vertex, we can also interpolate the normal. I mean, it's just a three-dimensional thing. And the normal is just a vector in 3D, just like colors are. So we can interpolate the normal for every point and then compute the lighting here. If we have the normal and the position, again, we can compute the light per point on the surface. This is also sometimes referred to as per pixel lighting. Okay. So, and per pixel lighting is, funny enough, a shading and lighting technique. Okay. So, and here's an example of what this looks like. Okay. So here we have a facial mask, and I use Phong lighting in each and every of these examples. Okay. So Phong lighting here, and Phong lighting here. Okay. I just use different shading techniques. There's Gouraud shading, Phong shading, and there's also flat shading. That's another alternative. That is, how do we interpolate the color of one polygonal object? We just pick a random vertex. We just pick one of the 2 or 3 vertices, or how many vertices our polygon has, and just use that color. Okay, that's referred to as flat shading. Okay, here we get the flat shaded objects. So I computed the lighting for all the vertices and just picked one vertex. Okay, so what this means is, well, we get flat, we get a constant appearance across the polygon. Well, because we just picked one value at random. You just pick the first or whatever. Okay, so, but it still uses Phong lighting. Okay, the lighting computation that I did for this one vertex was this ambient plus diffuse plus specular. Okay, next approach here is Phong lighting combined with Gouraud shading. So in this case, I compute this lighting again for each vertex, but interpolated the vertex values. Interpolated the colors in this case. Okay, and here finally on the right, and let's get out of the way, finally on the right you see Phong shading combined with Phong lighting. So the two obviously go together, but they don't have to go together. So what do you see? Well, you see it's smoother, right? So basically you gain functional degrees this way. Yeah. Which one is preferred? In general, I guess you would want to choose either this here or that one. Well, this one, if you want to visually preserve this polygonal structure, which is sometimes something that you want in your object, and you would normally choose Phong lighting combined with Phong shading if your object is approximated as polygons, right? Notice that the silhouette still shows that we have this sampling. We have these linear edges, but it's an approximation of a smooth surface. So we want to hide this approximation and want to actually, at least in the lighting, show the smoothness of the surface. Okay, then you would use that one. So why does Gouraud shading even exist? Well, it's more efficient. Okay, so why is it more efficient? What's the point? What's the difference between interpolating colors and interpolating normals? None. So that of course doesn't make a difference. If we interpolate 3 values and say, oh well, that's RGB, or we interpolate 3 values and say that's XYZ of a normal, that's of course the same performance. But we need to then perform the lighting computation, this ambient, specular, diffuse. We need to do this 3 times per triangle, even in the dumbest implementation, if we don't use shared vertices, right? Every triangle has 3 vertices, or if those are quadrilaterals, we need to do 4 computations and then just interpolate. Whereas here one, we need to do interpolate and then do the lighting computation for each pixel. Generally, you can assume that you have more pixels than you have vertices. That's not always true. If your resolution is super high and your triangles or whatever polygons you use tend to be very small, it might actually be the case that you generate fewer pixels than triangles, right? Think about a car in the city scene, and that's very far away, and it just gets mapped to a tiny space on screen. It might actually be the case that you end up with significantly fewer fragments on screen than triangles, but vertices. But generally, the number of vertices are lower than the fragments. Okay, so it's a performance thing. Today, with today's graphics hardware performance, you would probably use foam shading with foam lighting most of the time. Okay, any questions so far? Okay, let's just look at that more. Any questions about shading or texture mapping? The two topics of the stream so far. Okay, that doesn't seem to be the case. Then let's move on to the next topic, which is transformations. So what are transformations? Well, if you throw objects into your scene and render them, regardless of your rendering technique, I mean, it's nice to have them sit somewhere, but it would probably be even nicer to be able to transform them, move them around, scale them, rotate them, right? Throw some motion into the scene, so to say. And that not only applies to the objects, but it also applies to the camera itself, right? You want to move the camera around. Okay? So, and that leads to, well, a bunch of different spaces, as we'll see in a second. So there's the viewing, there's the modeling space, projection space, and then there's ultimately the viewport, and there's an analogy to a couple of things in reality. Okay, but first things first. What do we do when we build an object? Let's say we model an object. We use some creation tool to model an object. So that can be this sphere here, right? And so if I model a sphere in some tool, it might look like this. Okay, so I get knobs and dials to fiddle around with these things. So I might see the underlying structure. So I see that it's made out of these quadrilateral, which in turn are made out of triangles, and I see the normals that the software constructed. I see a bounding box. I can then work with it and play with it. Okay, and that an artist would use if they design a game. So if you the game, virtual environment, or anything in a computer setup, you generally have some sort of editing tool where you work on each object separately, okay, or in some object separately. So again, let's stick with this idea of, so you have a computer game that plays in a city, I don't know, GTA or Cyberpunk or whatever, and you model things, right? You model the humans, you model the cars, you model buildings. Okay? Then of course you don't model the whole thing as one big giant thing. I mean, you're working on this as a group, but you start to model, say, cars. Okay, so I built a car for a computer game as a designer. So what would I do? Well, I open my modeling tool, and I usually start at the center, right? I would create some kind of frame of the car and then throw, I don't know, usually I guess four wheels around the car, and then I kind of build other things, doors, headlights, windshield, whatever. But my point is that I do this modeling in the car's local coordinate system. Excuse me. So what is that supposed to mean? It means that I put the car in the center of my screen, or roughly in the center, and then I would say, well, the front wheel goes, I don't know, 2 meters to the front, and the back wheels goes 2 meters towards the back. So, and then whatever, some space to the left, and then done. Okay, so, and that's kind of natural, right? I mean, you probably wouldn't like type this in or so, but you would just drag it around in your modeling tool. But nonetheless, if you create a new wheel, it's centered somewhere, and then you place it somewhere. And that placement happens in relation to the car, right? You wouldn't model a car relative to the Earth's core, right? I mean, you could technically do that. There's nothing inherently wrong with it. You could say, well, my car is placed here in Duisburg, so its coordinate relatively to the Earth core is like, I don't know, 8 kilometers here, right, along some, I don't know, spherical axis, psi-phi, and then I move this 8 kilometers and then whatever, 1 centimeter up. Technically that's possible. It would be super inconvenient, right? So what you have is, what this means is, if you build 10 cars, you have 10 separate coordinate systems, right? One coordinate system is at the center of one car, and then the other one. If I place them in one common scene, they would all kind of superimpose each other. They would sit inside each other, right? That doesn't make any sense, right? So what I need to do is I need to place these cars somewhere, right? I need to transform them around, and that transformation means that I have a what we call local model coordinate system. So every model has its own coordinate system, right? And then we have the world, which is, say, my city. I got this cyberpunk game, whatever, and I want to place the car somewhere inside the city. So, and the city has its own coordinate system, and the coordinate system of the car might be in meters, right? Which is kind of convenient, right? 5 meters to the front. If you design a city, you probably want to design it in kilometers. Okay, so it's not only that I need to place this somewhere, meaning translate it, but I also need to scale it, right? 1 unit in my car's coordinate system would be 1 kilometer in the city, so that's a pretty big car. So you see that there's, besides animation, there's another need for transformation, and that is we need to transform coordinate systems from one system to the other, okay? And as I already said, so there's generally this notion of an object coordinate system or a model coordinate system. That's basically the same. Those are 2 interchangeable words. Model coordinates, object coordinates. So your object, your model has its own coordinate system. And then we have the world that has also its own coordinate system. The city itself, by the way, I mean, it's not something that you model as one piece, right? It's just, it's a bunch of buildings that you model that again have their own coordinate systems and you would place them somewhere, okay? So we need to transform things from one coordinate system to another. And here are simple examples of that one. So we have a bunch of spheres, we have a bunch of rings, or we have a bunch of dogs, I guess. And they're all the same basically. So this is just one geometry, one ring geometry, one sphere geometry, just with different colors. And again, one dog geometry, just with different colors. And transformed, rotated, maybe scaled, and translated. And the same happens in 2D. So if you use 2D modeling, say you want to design a circuit, you have your widgets, right? A diode, a capacitor, a resistor, whatever, and you place them somewhere. So each of these things has its own 2-dimensional coordinate system, and we want to place them into a common 3-dimensional coordinate system. So we need to map from object to world. And there's other mapping, as we'll see in a second, that we need to apply before we see things on screen. Okay, so what does it take? What kind of transformations can we imagine? Okay, what can you imagine? What can you do to an object? Okay, so let's look at things. Let's again start with our world, literally, the solar system. And let's take this very simplified, not at scale model here. So we have a sun, we have some planet orbiting the sun, we have another planet orbiting some, happens to be Earth, and there's a moon orbiting Earth. So what do we have here? Well, we have translations and rotations, okay? So the motions that the planets do are rotations around the sun. Let's pretend for a second that they're actually circular, okay? So we rotate in a circle. Another translation that we have is, well, transformation that we have is translation, right? We want to shift things around. So for instance, we want to shift Earth out of sun's core. Good idea if we don't want to get vaporized right away. Okay, so that's another type of transformation, translation. What else can we do? We can scale things, right? If we have like a thing here, a big thing, this, well, here, right? We can scale that down to a smaller thing. The thing happens to be a quadrilateral here. But you can also use non-uniform scaling. It means I can scale its width differently than its height, and then we get different scales versions here. Okay, so we got rotation, we got translation, we got scaling, and I just want to present one more, which is shearing. That is probably not that commonly used, but we'll later on see that shearing is a very important transformation. What does shearing mean? It means we take an object, hold it on one side and pull it on the other side, okay? So this guy here, for instance, sheared, so then it gets, well, sheared, stretched, whatever you want to call this. So that's yet another transformation, okay? And those 4 are really the important transformation that we care about. Now I have to get a little bit mathematic here, and I need to give those things names, or need to call them by their proper names. Okay, and I want to group them so that we see that they have certain similarities. So what you see here is scaling and shearing. So that's what I talked about, right? We also have the translation here, and we have the rotation here. So those are the 4 things: translation, rotating, scaling, and shear. But there's other things on top of that. Let's talk about those. There's reflection here. Okay, sometimes we want to reflect things, for instance, in a mirror, I guess. Okay, and reflection happens to be just a special type of scaling. So it's a scaling by a negative number. We'll later on see more about that. So this is why they end up being in the same space. So they're linear mappings. Scaling, shearing, and reflection is a linear mapping. Okay. Rotation is also a linear mapping. And then there's identity. So this is basically doing nothing. Why is doing nothing important? Well, we'll see that often you want to do nothing. Okay, so this is also a transformation. You can think about this as a addition of 0 or multiplication by 1. Okay, but it's still a multiplication. A multiplication by 1 is also a multiplication. So all of those fall into this category called linear transformation. Okay, and then we've got what is called a rigid transformation. Okay, so in a rigid transformation, you see that identity is a rigid transformation. As a matter of fact, identity is in all those classes. Rotation is rigid and translation is rigid. What does this mean? Well, it means if you take an object and you don't want to destroy it, you don't want to change its shape, so to say, you can still shift it around, translate it, and rotate it and do nothing to it. So all of those are rigid transformation. And then there's what's called similarity mappings. Those are the rigid transformations. All of those are similarity mapping plus isotropic scaling. So basically just increasing the size, zooming in or out. Translation plus rotation plus zooming in and out uniformly, that's called a similarity mapping. And you see that there's certain overlaps. But there's also certain other things. For instance, notice that translation is absent from the linear mapping. So everything I talked about here is linear, except translation. So that takes a special role. All of our mappings are fall into this realm of affine mappings. Okay, and I guess linear is something that you know. Rigid is probably either known or at least it's, I guess, intuitive. Similarity is also something that's not hard to grasp. Affine mapping is something that's often skipped at school. Affine mappings. Some schools teach it, some don't. So we need to talk about that certainly. Before I start with that, I have to get even a little bit more mathematical. But don't worry, it's not going to be a big deal. I just need to repeat a few linear algebra basics, like super basics. Okay, so don't worry. So first of all, we need to I need to introduce the term basis. So what's a basis? Well, I mean, there's a lot of theory to that. I just want to keep this simple here. So it's a minimum set of vectors that define a space. Okay, so for instance, for 3D space, a possible basis, the standard basis, it's called, are the x, y, and z axis. Okay, so if I use x, y, and z as an axis, okay, so here's the x vector, y, z axis, I call that a base. Why is that a base? Well, because it's a minimum set that allows me, if I combine them together, so just multiplying each of those basis vectors with a scalar, with a number, and then adding them all together, I can reach every point in the volume. Okay, so this is then called the span. So whatever I can reach with a set of vectors is called the span, and the span of this basis is simply R3. It's a three-dimensional space. Okay, and there happens to be this strange coincidence, so to say, that if I use coordinates x, y, z, right, say 3, 2, 1. I have to multiply this vector with 3, this with 2, and this with 1 to get to the point 3, 2, 1. Okay, so the standard basis has this nice property that its coordinates equal the points in the space. Okay, well, I guess it's not a big deal, but this is just how this works. Okay, and this becomes important if we change the base. So there's nothing wrong with choosing another base. So for instance, we could rescale one base vector. We could say, okay, our first vector is 2, 0, 0, and this is 0, 1, 0, and this is 0, 0, 1. So I basically changed this here to 2. Then a point that had previously had the coordinates 4, 1, 1 now has the coordinates 2, 1, 1. Okay, because this basis vector is twice as long. So 2 times this thing ends up being 4, having length 4. Okay, so we can choose different bases and get the same spans. We get the same or different vector sets and get the same spans. So they are bases for the same spaces. So long story short, bases are not unique. We can choose others, and we choose the standard basis. Okay, now that's a basis, egg 1. Egg 2, what's a linear mapping? Well, a linear mapping is a mapping that's linear. Okay, and in this case, I choose a linear mapping from R3 to R3. There's tons of linear mappings, but this is what we care about. We care about something that maps things, which I call points for a second, that maps points in 3D space to 3D space. So for instance, a rotation, right? It takes a point as input, rotates it, and outputs a point. Or a scaling. It takes a point as input, scales this thing up, outputs a point. That's a mapping. Okay, R3 to R3. So what makes a mapping a linear mapping? Okay, and here's the short path. Again, look this up in your textbook. You should have had that at least in your bachelor's classes. But here's a quick refresher. What's a linear mapping? A linear mapping is can be defined in multiple ways. But one way to define it is to require two properties. One is the addition property, and the other one is the scalar multiplication property. What does it mean? It means if I take two things, all right, say 2 points, okay, and let's just call them P and Q, okay, and I add these 2 points together, right? So basically 1 point here and 1 point here. So I get a new point, right? P plus Q is some point. And I apply a mapping to it. For instance, I rotate it. Yeah? Then the result of that rotation should be the same as if I've rotated the first point, rotated the second point, and then added the two together. Okay, for rotation, I guess that's clear, right? So if I just take 1 point, another point, right? I get this one here, and then I rotate it. I should get the same as if I took that point, rotated, took the other point, rotated, and then added them together. Okay, so that's the first property, and we can see that rotation is linear. Well, not really see, but you can probably guess it. Okay, so that's property 1. Whatever this add means, right? In a very general mathematical sense, this addition here might be something that is more awkward than you would think, but it has to follow certain rules, this addition. So the other thing is this scalar multiplication property. So if we take a point and we multiply it with a scalar, so P is this thing in our vector space, which I happen to call point here. Okay, so that's a little bit mystic. Okay, but alpha is simple. Alpha is just a number. Okay, it's 42.8 or so. So this here is something that is potentially complicated, but alpha is always simple. It's always a number. Okay, so what happens if I multiply a vector by a number? Well, I usually probably for points, I would just define this as a component-wise multiplication. So I would take x, y, and z and all multiply them with alpha. Okay? But this multiplication again needs to be defined somehow. So, and now what's the second criterion for linear mapping? It's if I take my vector space element, point, multiply it with alpha, I get some new point, and then I transform with whatever my transformation is. And that again has to be equal to the transformation of the point alone, and then multiply it with alpha. Okay, if these two things hold, then my mapping L is a linear mapping. If one of those two is broken or is violated, it's a non-linear mapping. As simple as that. So, what's the consequence of that one? Why did I repeat that? There's an interesting consequence, and that is a linear mapping cannot change the origin. What's the origin? Well, the origin is a special point that you also need to define. When you define a vector space, you need to define a zero element. In real numbers, the zero element is simply like literally the number 0. In our general R3 vector space, it would be the origin of the coordinate system. So the vector that has coordinates 0, 0, 0. Okay, nothing too hard. I just put this arrow on top of that to indicate that this thing is not the number 0, but it's the 0 element in the vector space, which is really the origin for all intents and purposes here. So, and a consequence from those rules is that the origin under a linear mapping cannot change. Why is that the case? Well, it's pretty straightforward to see from the second condition here. So there's a special property that needs to hold for multiplication, and that is that if you multiply something with 0, it stays 0. That's pretty much the definition of the 0 element. If you multiply with anything, the result is still 0. That's pretty much the definition of a multiplication. So what that means is if P is 0, then alpha times P is obviously also 0. So whatever I choose alpha, I always get a zero out. So the left side here is always going to be 0. So, and what does this say? Well, if regardless how I choose alpha, I always get 0 out here. So L of 0 has to be, what does it have to be? Well, it has to be L of P times alpha. Okay, so now let's do the following. Let's see what happens. Well, what happens is I get some transformation of my P here times alpha. Okay, so and let's say this, I don't know what this transformation ends up, but let's choose alpha as 0. Okay, let's just choose that as 0. So again, that's the number 0 now times a vector, which means this here will be 0. I can pull the alpha out. Now I pull the 0 out. Now I get 0 times some transformation. But again, by definition, 0 times something has to be 0. So when I choose alpha at 0 and choose any P that I want, this means that this here, that L of 0 has to be 0 times something, and that's also 0. So long story short, the origin can change. Why is that interesting again? So why would you care? Don't you just want to do computer graphics and don't want to learn about silly linear algebra stuff? Well, it means you can't translate things. What does that now mean? It means translation doesn't work. Shifting things around doesn't work. If I want to design a mapping that shifts things around, say I want to say, okay, now the whole world please move 10 meters to the right. That automatically means that the origin also needs to move 10 meters to the right. I mean, everything should move 10 meters to the right. But if the origin can't move, I can't move. Okay, so that's basically the proof that translation doesn't work, at least not as a linear mapping. That sucks. It sucks particularly because linear mappings are super nice. So here's a nice property, and that is you can represent linear mappings super easy by matrices. So what does that cryptic formula at the top mean? It says for all else there exists an M, and M is a matrix. It's a 3 by 3 thing for our 3-dimensional points, such that L of P equals M times P for all P from our vector space. So that's a cryptic mathematical way of saying any linear mapping can be represented as a matrix vector product. Okay, and that's nice because, well, matrices are just 3 by 3 arrays, and after all, we're computer scientists, at least most computer graphics folks are, if you're on the implementation level, and 3 by 3 array is easy to handle, and a matrix vector multiplication, we can figure that out how to do it. Either you know it or you look this up in the textbook. Okay, so that's cool. Why is that the case? Well, we can actually very easily prove that. We could say, well, okay, if we've got this awkward L of P, like any linear mapping L of P, then what is this? Well, P can be represented as X times E1 plus Y times E2 plus Z times E3, which is, I guess it's just the definition of a point in vector space. Remember, base vectors, X, Y, Z multiplied with bases. Okay, now I apply linearity constraints. One was I can pull I can separate the plus things. Like I can separate L of X times E1 out plus L of Y times E2 plus L of Z times E3. So that was the first linear rule. And then I apply the second one, which means I can pull a scalar out of a multiplication. So, and once I've produced this thing here, so this is nothing but a matrix vector product, okay? And I basically take L times a vector, X times a vector, namely L times E, Y times a vector, namely L of E2, and Z times a vector, namely L of E3. And that's just a matrix vector product, right? That's taking X, Y, Z and multiplying with a matrix. And what does the matrix look like? Well, I just throw L of E1, L of E2, and L of E3 into a matrix, okay? And that sounds like a pretty straightforward thing, right? But it's very important, and it's something that's often overlooked. And even though it's a little bit silly, but it can't be overstressed how important that particular property is, that I can take a mapping and apply it to the base vectors, one after the other, okay? I get new vectors, right? If our mapping maps vectors to vectors. Okay? So I apply the mapping to the base vectors, each of them separately. I get 3 new vectors for a 3-dimensional space. Okay, and now I just take these 3 vectors and put them into a matrix. Okay, just like literally take the numbers out and write them into a matrix syntactically, and I get this thing out that is now one unit. It's one matrix. Now if I take that thing and multiply it with anything else, I get the same as if I would have taken that anything else and transformed it with L. Okay, so why is that cool? Well, we'll see in a second. Why that is cool, and it's very useful. Students always forget it, do crazy complicated things in computer graphics, whereas it's so simple to do things. Okay, so let me just give you an example. Let's say I want to map one transformation onto another. Why would I need that? Remember I said we sometimes have things modeled in one space and sometimes have modeled them in another space, object space, word space. So you'll later on see why for that one it's obviously necessary to map things onto another. So I have coordinates in one space and I have coordinates in another space, and I want to know how to map them from one to the other. Okay, so how do we achieve that? Okay, let's say, okay, first, and a little bit about notation. So the curly brackets here are just set of vectors, and where are the other brackets? The other ones, the straight brackets. Let's just call them brackets. Okay, those brackets here are a matrix. Okay, so we've got a matrix of 3 vectors, and we've got a set of vectors. Okay, now let's look at that P1, P2, P3 thing first. So how can I map E1 to P1 and E2 to P2 and E3 to P3? How could I potentially do that? We ultimately want to map P's to Q's, but let's take an intermediate step first. Okay, how could I do that? Well, I could just take P1, 2, and 3 and put them in a matrix and then multiply them with E1, E2, and E3. Okay, let's just do a sanity check here quickly. Like, what happens if I multiply E1 with that thing? Well, E1 is 1, 0, 0, right? It's P1's first element times 0 times 0 times plus the second one times 0 plus the third one times 0. So it's just P1, first element. So next row, again, 1, 0, 0 times the second coordinate of P1 times 1 plus the second coordinate of P2 times 0 plus the second coordinate of P3 times 0 also happens to be the second coordinate of P1, and then the third one. Okay, so and now we repeat this process. So multiplying the unit vectors with the matrix that is P1, P2, and P3 transforms the unit vectors to P1, P2, and P3. Not a big deal. Again, it doesn't have to be a big deal, okay? But now we have a matrix. So, and we can do the same funny trick with the Q's, right? If we throw Q1, Q2, and Q3 into a matrix, and we multiply those with the base, we also get Q1, Q2, and Q3, okay? Why am I doing that? I want to get from P1 to Q and not from E's to the P's and E's to the Q's. Well, it happens to be that there exists a thing that's called a matrix inverse. Okay, you've probably heard about matrix inverse. They invert the transformation. So that said, if the matrix can be inverted, let's not talk about those details here. Let's just assume we can invert those matrices so they're linearly independent. So if I take my P1, P2, P3 matrix and invert that by some crazy approach, it inverts the transformation. That's just like multiplying a thing or dividing the thing, right? It just inverts, it undoes. So if I invert P1, P2, P3, the whole matrix, I get a transformation that now maps the P's to the E's. Okay, because previously it mapped the E's to the P's. Okay, now why would I care? Because I can now put this all together and I can take my input, first multiply it, my input is RP's, yeah? First multiply it with this inverse matrix, I get the E's, and then multiply that with this Q matrix here, because the E's multiplied with the Q's gets me the Q's. So to make a long story short, if I take P1, P2, P3 inverse times Q1, Q2, Q3, I get one matrix. A matrix times a matrix is again a matrix. Again, I assume you know that from linear algebra. Then I get one transformation, which happens to be a linear mapping. Okay, we're still linear. We're doing matrices, and we know that any matrix is a linear mapping. Any linear mapping is a matrix. Well, technically, I only showed one direction, but the other one is also easy to show. So with that one, I can take any three vectors and transform them to any other three vectors. Okay, as long as this inverse exists. Okay, so that's an important restriction here. So it's not any three vectors. Let's say the inverse has to exist. So for instance, they cannot be 0, right? So again, I can't transform 0 to anything. So the story holds here. Why is that important? Just wait a few minutes. Just try to not forget this, okay? Because it's super important. Okay, now let's look at, I said we have scaling, we have translation, we have rotation, we have shearing. Now let's look at these things. What do the matrices look like? If any linear mapping has its matrix representation, what do they look like? Okay, let's start with scaling because it's easy. Okay, that's a scaling matrix. If we want to scale the x direction by alpha, y direction by beta, and z direction by gamma, we just end up with a matrix where we set everything to 0 except the diagonal, and we set the first one to alpha, second one to beta, third one to gamma. If we want to scale everything the same, say by 2, we end up with a matrix that's simply 2, 0, 0, 0, 2, 0, 0, 0, 2. Okay, if I multiply a vector with that one, guess what happens? It's twice as big in every direction. Okay, so that's scaling. I guess that's easy to say. You can also see that scaling by 1, which means do nothing, is just the identity matrix. So the identity is also a special case of scaling by 1, which means do nothing. So next one is shearing. What's this? Shearing again was this awkward pulling notion. And there's a lot of things you can pull. So you can hold the bottom, you can pull at the top. You can hold the front, you could pull at the left. You could hold the left, you could pull at the right, I guess, right? And then you could combine this. You could hold the front and pull, hold the top and pull at the front. So you can do all kinds of things. A total of 6 things you can do. Okay, depending on where you hold and where you pull. Okay, so this basically gives you 6 choices, and these 6 choices are kind of all the other elements except the ones in the diagonal. So if you take, if we go back to scaling here, you see those have to be 0, and those are responsible for scaling. If I leave those as 1, so I don't do any scaling, and I just modify one of those other 6 values, then I get a shearing. Okay, so for instance, if I want to shear by holding the bottom and pulling at the top, okay, then I need to modify this value here. And if I want to shear by a certain factor, say s, I throw in an s here. Okay, so what happens if I multiply vectors with that matrix? So let's just do a simple example here. So if I multiply the x vector, the x-axis with this matrix here, nothing happens. Okay, so if I multiply this with 1, 0, 0, it stays the way it is. If I go a little bit off the origin, if I move a little bit up, so the higher I go, the more I want this to be pulled. So this has to be depend on the y coordinate, this pulling thing, right? At least for that type of. And that's what I get here. So if I say, okay, well, take s times the unit vector plus e2. So I basically move a little bit to the right and a little bit up. Then the further I go to the right, the further I get pulled. Okay, which kind of makes sense, right? We want to pull to the right. So I basically get here a higher x coordinate, the higher my my input coordinates, and then in z direction nothing changes again. Okay, so what this tells you is quite interesting. That is, and then again, if I like throw the s in somewhere at the other positions, I kind of pull in z direction and in other direction. So what's kind of curious about this is that we're kind of done. Yeah. So I've basically exhausted all positions of my matrix. Oh, we got a question here. When do you need to go down to this level? If you're coding in Vulkan, every time you do any type of transformation, Vulkan Vulkan as such, as a low level API, I'll get later on why I say low level API. Any of your transformation are just setting arrays of matrices. So there's no helper functions whatsoever in Vulkan to do any type of transformation. So if you want to rotate, translate, scale anything, you end up with a nice call that says, okay, give me a 3x3 array. And so you have to figure that out. So every time you transform something, you have to get to exactly that level. If you're not coding in Vulkan, say you're coding in OpenGL, DirectX, same thing. You have to specify those matrices. If you're coding in a higher level thing, say you're using whatever, a game engine such as Unity or Unreal, you probably have an opt that says, okay, well, rotate by 90 degrees. Okay, so you might say, okay, well, I don't need to know this, which is a perfectly fine thing, right? If you're driving a car, you need to know how a clutch works. You don't need to know how a clutch works. You just need to hit it and then put in your gear. But there's one issue with that approach. And that is that if you don't know the basics of these things, you don't know, for instance, why I can't translate my object. Okay, as I said, translation is not a linear mapping, as I was just trying to get at, shearing are all off-diagonals. Scaling are all diagonals. Where's rotation? Where does rotation go? If any off-diagonal is shearing, if any on-diagonal is scaling, what is rotation? We don't have any degrees of freedom left here, right? And we can combine the things, right? If I put in this matrix shearing and rotation simultaneously, shearing and scaling simultaneously, well, I get an object that is scaled and sheared. And where's the rotation? So that's still something, even if you have a rotation slider, that you need to know. Okay, and I'll also tell you in a second why you need to know that. So where does rotation go? Well, it turns out rotation goes here. So this is an example of a rotation around the x-axis. And now you see that I use those four parameters to rotate. I mean, the details, you can derive the details. I'm not going to do this here, but it's a combination of cosines and sine. And what does this mean? And again, this boils down to the question that we just had. Why do I need to learn this? Or why should I learn this? Well, because now you know that a rotation is nothing but a combination of shearing and scaling. And that is, first of all, interesting, right? That you can rotate an object by rescaling it, so stretching it, and then pulling on sides, and that happens to be the same as a rotation, right? A rotation around the x-axis means I have to rescale the object in x and z, to blow it up in x and z, and then kind of pull it, and then I get back. So you can say, well, okay, that's nice to know, maybe if I'm a mathematician or if I'm into linear algebra, but again, stick with me for a second. That's going to be very important if we do certain other things to know that this is a combination of these operations. So long story short, rotation, you could say rotation isn't really something on its own. It's just a combination of scaling and shear. Here's the thing for the x-axis, just for completeness sake, this is what this looks for rotation around the y-axis. And this is a rotation around the z-axis. Notice that it's always going to be sines and cosines, sometimes with negative, sometimes with positive sign. And one axis always remains 0, 0, 1, 0, 0, 1, right? If I go back here, you see that this x is in the center, and if I go one further back, you see that it's to the right, which is no surprise, right? If I rotate around the x-axis, everything on the x-axis stays the same. If I rotate around the y-axis, everything on the y-axis remains the same, and if I, well, rotate around the z-axis remains the same. Okay, that shouldn't come as a huge surprise. So now we know how to rotate around the x and z and y. How do we rotate around an arbitrary axis? Well, we'll get to that in a second. Let's just stick with these. So first of all, what's the inverse of a rotation? How do I rotate a thing back? Okay, well, you could rotate by the negative angle, right? If you rotate 45 degrees, and you can undo this by minus 45 degrees. But let's say I don't know anymore how this was constructed. Right? Say I'm just given the rotation matrix and I want to undo the rotation, right? So for instance, because I want to get my spaceship to be in its original orientation. Well, we already know that any matrix that can be inverted will undo the transformation. So what you could do is take your rotation matrix, compute the inverse, and be happy with that. Now it turns out an inverse computation is quite costly. Okay, but, and here again we come to this question about why do we need to dive so deeply into this? Because we need this to write high performance code. Because it turns out a rotation is what's called orthonormal transformation. And then one has the property that its inverse equals its transpose. Now what's a transpose? Transpose is pretty simple. Let me just go one way. Transpose is just flipping the thing on its diagonal. Okay, so in this case it means just basically throw a minus in front of this sign and remove the minus in the other one. That will flip this. Okay, and that's way easier to just remove one sign and plug it here than to invert this whole matrix. And it's also numerically more stable, but it'll invert that transformation. So what's an orthonormal base, or what's an orthonormal transformation? It's a transformation. To keep things here simple, I just give you the syntax how you could detect an orthonormal matrix. An orthonormal matrix is a matrix where every row and column is perpendicular to every other row and column, and they all have length 1. So let's see, are they perpendicular? Meaning that they point into perpendicular direction. Well, let's say 0, 0, 1, and we've got 0 here, and those two have values. So they look pretty perpendicular to me. One points into 1, and the other one doesn't point into 1, but into x and z. That's the case. And this one here, well, it's probably a little bit harder to spot that that's perpendicular. But let's just believe it's perpendicular, and curiously, if you look at instead of the rows, at the columns, you get the exact same vectors. Okay. Good. Now, do they all have length 1? Yes. 0, 0, 1 has length 1, so that's, I guess, pretty easy to see. But sine alpha, cosine alpha 0, does that thing have length 1 for every alpha? Right? I mean, this appears to be independent of alpha. And yes, that's the case. How do we compute the length? Well, it's x squared plus y squared plus z squared root over that thing. So what we get here is sine alpha squared plus cosine alpha squared, let's skip 0 squared, root of that. Does anyone remember what alpha squared, what sine of anything squared plus cosine of anything squared is? It happens to be 1. That's sort of by definition, right? Sine squared plus cosine squared of any parameter is 1. Root over that is also 1. Okay, so voila, orthonormal matrix. Translation can be efficiently computed by the means, inverse can be efficiently computed by the means of a transpose. That's the thing that you only figure out if you look a little bit into the underlying theory. Okay. So what else can we do? So now what I want to do is I want to rotate around an arbitrary axis of rotation. So here's kind of the nutshell approach to how do we do this? Like what's that supposed to say? Okay, so what do we have? We have an orthogonal basis. So we have something that's RST. Okay, so what is RST? Okay, let's say I want to rotate around an axis R. I don't want to rotate just around the x-axis, z-axis, y-axis. I want to rotate around the axis of my spaceship. I mean, it's pointing this way, right? And I want to rotate around that axis. Is that so much to ask for? No, it's not. Let's figure out how we do this. Well, the way we do this, we take the direction in which we're looking, and we need a second parameter, the so-called up vector. So if we just say, okay, spaceship flies into this direction, and I want to rotate by, say, 45 degrees, I first need to know, like, where is up, okay? And if you don't want to tell me where up is, I can just compute my own up. How do I do this? I just need a vector that is perpendicular to the viewing direction. Okay, I say this is now where up is. Okay, how do I get a vector perpendicular to anything else? I compute a cross product. The cross product of two vectors is a vector that is perpendicular to the other two. Okay, so and again, why is that the case? Look this up in linear algebra. So what is the second vector that I compute a cross product to? I can choose any one that I want, as long as it's not pointing in the same direction as R. So I'll just choose E1, which is really literally a random choice. I could have chosen any other vector. I just pick E1 because it's the first one in the base. So I compute R cross E1, and now I might, so this will work 99% of the time just fine. Probably 99.999% of the time. Except if I just for some crazy reason, R happens to be E1. I happen to fly with my spaceship into X direction. In that super rare case, I'll choose anything else that is perpendicular to E1, and that's E2. Okay, so long story short, I first compute a cross product with E1. If that happens to result in chaos, meaning 0, then I compute a secondary cross product with E2. I could also have chosen E3. So I just pick any other vector that happens to be not E1, for Christ's sake. So I'll just pick E2. In the bottom line is, after this, I have a second vector S that is perpendicular to R. And I don't really care how that came into being. Okay, just one of those two will work, has to work. So and then I take these two things, R and S, again compute the cross product, and get a third vector. Since R and S are already perpendicular to each other, I get a third vector which is perpendicular to the two. So with that, I now have R, S, and T. So I've basically blown up one vector into 3 vectors. And what this is called is it's called creation of a coordinate frame. So I started with one direction, and I created a whole coordinate system around this direction. Or in other words, I created 2 vectors that are perpendicular to the first one. What I have created now is I have created a base, or a basis, that is, again, orthogonal. I have an orthogonal basis. All vectors are perpendicular to each other. Their span is, again, the entire 3-dimensional space. So I have a local coordinate system in, say, my spaceship that I want to rotate. Then just for simplicity's sake, I normalize them. So I give them length 1. So I basically divide each of those by their corresponding length. And then I do a base change to RST, and I've got my transformation matrix M. Whoa. What is that supposed to mean? What is a base change? Remember when I presented the slides that map P1, P2, and P3 to Q1, Q1, and Q3? That's a base change. So I would basically, I built a matrix that changes vectors in one space to vectors in another space. And now what I want to change vectors in E1, E3, E1, E2, E3 to RST space. Okay, what do? I multiply them. I already said, remember my PQ examples? I said, okay, just take the vectors, in this case RST, put them in a matrix and invert that matrix, and you get something that changes the unit vectors into RST. RST into the unit vectors, so the other way around. Okay, it changes anything that's in direction R into unit vector 1, anything that's in direction S into unit direction 2, and anything that's in direction T, vector 3. So that's my base change matrix here. Okay, how do I use that for an arbitrary axis of rotation? Now, if I have an arbitrary axis of rotation, what I do is, first of all, this axis might be not in the origin. So I first translate everything into the origin. How do I do this? Well, I just pick one point on the axis and shift everything. I haven't talked about translation so far, but let's just say we get this done. Then I use my base change. So this will basically map my coordinates RST into X, Y, Z axes. And then I just rotate around the x-axis, because this happens to be where my R is now mapped to. Then I perform the inverse of that transformation. So basically, and that happens to be a rotation as well, by the way. So this base change is a rotation. But I do the inverse, so basically shift everything back into RST space. And then I perform the inverse of the translation, which is just translate by minus that thing. And that then rotates around an arbitrary axis of rotation. So again, arbitrary axis of rotation, I want to rotate here. I first of all shift it to this origin, bring it to the original XYZ axis, rotate my rotation that I want to do around the x-axis, then put it back into its rotation and shift it back. And what I ultimately did is, after all of this craziness, I rotated my spaceship. Now you can say, well, that's a ton of work just to get this silly rotation to work around an arbitrary axis. Yes, it's true, but here's the beauty of it. And again, that requires a little bit of insight into linear algebra. What are these things? We've got our rotation, So what do we have? We have a translation. We have our base change, which is a matrix. The translation, as we'll later on see, is also a matrix thingy. It can't be right away a linear mapping. It can't be just a normal matrix, but it's kind of a crazy matrix thing. But it's also just a matrix multiplication. This here is a matrix multiplication. This here is one, right? Rotation around x-axis is on one of the slides. This here is just the multiplication of this inverse matrix here. And this is also the multiplication of this inverse matrix-like thing. So on the bottom line, we have matrix times matrix times matrix times matrix times matrix times vector that we want to rotate. Now, the cool thing about matrix and matrix multiplication, we can just multiply them all together. So in the end, we get just one matrix times vector. So to make a long story short, all of this craziness just needs to be done once, and we've got our axis of rotation matrix. And it's as complicated as any other rotation later on. We just have the complexity into constructing in constructing this matrix for once, and then we're just fine. Okay, so this is how you rotate it on an arbitrary axis. Again, why do you need to do this? Well, if you do Vulkan, DirectX, OpenGL, it just says, okay, well, you want to do a transformation, please give me this matrix here. You need to know how to fill this. And you fill this by this product of these 5 matrices. So I think it's time to talk about translations. Okay, so how do we do translations? So what I want to shift everything. Okay, so why not just throw in our translation by x, t, and z in here? Well, it turns out that doesn't work. So this slide is incorrect. Well, if those are our parameters, if this is where we want to get at, this matrix will not do the trick. So, and why can this not work? Because translation is not linear. It changes the origin. So it doesn't work. Here, that's a sad truth. So it doesn't work. So we need to move beyond linear transformation. We need to move to affine transformation. So what's our affine transformation? Technically speaking, they're just literally linear transformation plus this translation, I think. Okay. So, and remember, we had this slide here. So how do affine transformations work? So again, we can't shift the origin. So the trick is in affine transformation is don't shift the origin. We can shift anything else, right? Any other point can be moved around just fine, but the origin can never change. So the idea with the affine transformation is don't look at the origin. So that's literally the idea, at least not when you want to translate. Okay, so let's say, let's do the following trick here. Let's say I do shearing, right? And let's just, what was shearing? It was kind of pulling, like shearing in one direction, right? It was kind of pulling on this thing. So if I would shear in the x direction, as I did before, I would pull by a certain amount in x. And that is almost a translation, right? It's almost there, except that depending how high I am in y, I pull more or less, right? And as a matter of fact, if my y is 0, I pull not at all. Right? That's why it's a linear mapping, because it doesn't pull the 0 point. But if I move up a little bit, it pulls it quite a lot. And it's almost a translation, right? If I say shear by 5, it literally, at height 1, it pulls at a distance of 5. So, and that's the idea. The idea is to represent a translation as a shearing operation, and I'll only look at height 1, right? So what does this mean? It means when we're only dealing with this plane, this xz plane at height 1, we could construct a 3x3 matrix, a 3x3 scaling matrix, that if I only look at points in the plane, right, then I get my translation, because it's a shearing in 3D. It's a shearing of the entire 3D space, but then we'll translate this one plane by whatever my shearing degree is. Right? So if I just look at a smaller space as my matrices, I can do translation of this plane that's 1 away. Okay, and on turning this argument upside down, I can move to 4-dimensional coordinates and shear the 3-dimensional subvolume of the 4-dimensional space, which is kind of crazy to think about. But anyways, if I shear this 4-dimensional space, it happens that if I look at just the subspace at distance 1 in the 4th direction, I get a translation. And that's exactly how how translation works. We move to 4D coordinates and just set the fourth coordinate to 1. Okay, so we only look at xyz1. We don't look at xyz5 or xyz 34.8. We just look at xyz1. At least if we're talking about points. We treat the vectors a little bit differently. So that's where we look at xyz0. Okay, so we just add a fourth coordinate and we just put a 1 in there and just forget about it. Okay, and then how do we then transform things? So first of all, we use our normal things: shearing, translation, rotation. Now they have to be 4x4 matrices because we can multiply. Our input is going to be a 4-component vector and the output should also be a 4-component vector. So we basically have to blow up our matrices to 4x4, but that's not a big deal. We just put them into the 3x3 subpart and then make the rest 0, 0, 0, 1, 0, 0, 0, 1. Okay, that won't change the fourth part. Okay, so this is how we extend linear transformation. Now, where does the affine come in? Now, if I take the last column here and take the first 3 entries of the last column, remember that's shearing, right? Everything that's off diagonal is shearing. So if I put something into the first parameter, so this t, there's 3 component, it shears. What does it shear? It shears z along the x-axis. If I put something in the second, it shears z along the y-axis, and the third one is it shears z along the z-axis. Okay, it shears the fourth coordinate along the x, y, and z axis. The fourth coordinate is 1. It's always 1. We choose it to be 1. So if I throw something in there, it will shear everything in x direction by that degree. If I put something in the second one, it shears everything in y direction and z direction. So we get our translation. Okay, so that's the whole trick. Now what happens if I would have put in a 2 for some crazy reasons, right? What would have happened is I would have doubled all of my shearing, right? If I shear here and I shear higher, well, it moves twice as fast. So what we can later on see is if we put anything other than 1 into there, it ends up being a rescale operation. So if we want to get back to the original coordinate that we meant to use, we have to divide by the fourth coordinate, which is called dehomogenization. Okay, so because we have to then, since it's a scaling, we have to then divide everything down. So what is it with this strange idea of throwing a 0 into vectors? Well, if we throw in a 0 there and we apply shear, what happens? Nothing. Okay, if we make the w coordinates, as we call this fourth coordinate, if we make that 0, this t here will have no effect, right? It always gets multiplied with 0. And that's cool because it means translation doesn't apply to that one, which is exactly what we want. A vector doesn't have a position. A vector is just a direction. It rotates fine, it scales fine, it shears fine in 3D, but it doesn't translate. It just refuses to translate. And we achieve this by simply throwing in a 0 here. Okay, and then we can simply multiply our points and our vectors with this matrix, with this 4x4 matrix, where this part are just our regular linear mappings. This stuff we generally set to 0. We'll later on see that we can actually put in values here that are non-zero, and that ends up being projection. And we throw in the translation here, and we always put a 1 in here. So we don't use, we never use that code. Okay, and that's called an affine mapping. Okay, so now we get rotation, shearing, scaling, translation, and as you'll later on see, we also get projection stuff, or certain projection parameters stuff. Which is cool. We can now shift things around. We just, in the end, if we render the thing, we just divide by the fourth coordinate if that happens to be non-1. And even when we divide by the fourth coordinate, it happens to be 1, well, nothing happens. If it's not 1, we just dehomogenize. We kind of scale it back into its right plane. And if the fourth is 0, we don't want to divide by that. The division by 0 is not a good idea, but for a vector, we simply drop the fourth coordinate. Okay? So those are the transformations that we're interested in. Any questions about that part? Drink something in the meantime. So, doesn't seem to be the case. Okay. Well, either good or bad. Either everything's clear or my internet connection hasn't recovered and I'm just talking into void. Okay, so that looks good. So what else? What else can we do? What else is important to talk about when I talk about transformation? So what are we dealing with anyhow? Well, we're dealing with points, right? So far I talked about coordinates. I said where there's this car and you rotate that around and you scale that around. Oh, I got a question here. Is this all GPUs know how to? Well, yeah, it's almost pretty much it. Yeah. Well, I haven't talked about GPUs or rasterization in that regard. I talked about ray tracing so far in the last streams, but yeah, if you want to go to if you want to go to rasterization, which will be a topic of the future streams next week, you'll see that it's pretty much it. GPUs really can't do that much, and one of the things they can do are matrix vector operations. They can do a little bit more, but one important thing are matrix vector operations. Okay, so and what else does it take? I mean, if you're dealing with your scene, if you're dealing with your, say, coordinates of your car, what else do you want to do except for rotating it somewhere, placing it somewhere, translating, scaling it? And well, you probably don't even want to shear. that's again a very rare transformation. But as we've seen, rotation is effectively shearing, and translation is also shearing. So it's all shearing, it's except for scaling. Everything else is shearing. So it's an incredibly important transformation, even though you don't know that, or you didn't know. Now you should know. Okay, so positions, points are just basically transformed this way. What else do we want to transform? Well, how about colors? Should colors change if I move my object around? Maybe not. Well, they should probably change if I light it differently, but let's not talk about lighting so far. But the colors shouldn't change, right? What about texture coordinates? If I rotate an object, well, the texture coordinates should rotate along with it, but this happens when the vertices rotate. Okay, so texture coordinates also no-go. What else do we want to change? What else do we interpolate? Well, there's normals, right? Remember, we have our object. And when I rotate the object, then the normal also needs to be changed, right? If I have this object here, the normal is probably 0, 1, 0, so it's pointing straight upward into y direction. If I rotate my object by, say, 90 degrees, it should now point into x direction. So I need to adjust the normals. Long story short, those need to be adjusted. Normals are vectored, they aren't points, so we throw in x, y, z, 0, and we run them through the same transformation as before. No, that's not correct, even though I would say about 80 to 90% of the code that I can find on the internet does it exactly the same way, but it's still wrong, which is one of the warnings that I keep on repeating in my computer graphics lecture. Don't trust code regarding computer graphics that you find on the internet. Wait a second. Technically, you'll find this lecture on the internet, but this one's okay. No, seriously. So one of the issues with computer graphics, and I warned at the beginning of this stream, so if you can remember that or you watched the whole stream. So computer graphics code or computer graphics information are hard to debug. Why? Because you don't just generate 42 as a result, you generate an image as a result. In an image, if you just think about a 100 by 100 pixel image, it's tiny, right? 100 by 100 is super small on a monitor, but it's already 10,000 values. And those are red, green, blue values, so you get 30,000 values. And you don't just look at 30,000 values and figure out it's okay. So most of the debugging, as I said, happens visually. So you look at it, and once it looks fine, most people are pleased and say, well, okay, now it's good. And that's a bad idea, because it might just work in one situation, but in others it doesn't. And this is the reason why I find so many broken code on the internet, and that includes very reputable sites such as, I don't know, what is it, Stack Overflow or so. I see a lot of broken code there as well. And one of the things that a lot of folks get wrong is the transformation of normals. Just because if you do it wrong, it works pretty often, but not always. Okay, and it's up to a point that I found documentation of graphics APIs that do it wrong. Examples in the DirectX SDK, for instance, were wrong for quite a while. So what is it with these strange normal transformations? Okay, so let me give you a simple example. So let's say that's a geometry, okay, and that's a transformed version of that geometry. In this case, it's just simple. It's just scaled. It's just scaled in y direction. It's non-uniformly scaled. Okay, and now let me draw the normals here. let me draw the normals on the left, right? You see the normal is a vector that's perpendicular to the surface, and as you can probably see, they're all fine. So they're all perpendicular to the surface. Now what I did on the right was I transformed this this circle, and the problem holds in 2D as well as in 3D. So we can just do this in 2D. So I transformed the circle by non-uniform scaling, and if I apply the same non-uniform scaling to the vectors, that's exactly what they look. That was actually pretty easy. So I just literally took the graphic and scaled it down. As you can see, they're not perpendicular to the surface anymore, at least not everywhere. So some work. This one works, and also this one here would work if we would have the one in the center. But the others, I mean, this one's clearly not perpendicular to the surface anymore. It would have to be this, okay? Those are the proper normals. And there's a significant difference here, okay? So how do we go from here to here? So obviously normals cannot be transformed the same, obviously meaning from that image you can see, normals should not be transformed the same way as the positions. Okay, how should they be transformed? Well, the truth is the transformation isn't hard to compute, but it's not very intuitive. But I'll still quickly prove it. Then you will see that the result is correct if you trust the proof, which I suppose you should. But the outcome is not very intuitive. Okay, so let's say, what is a normal again? A normal is the thing that's perpendicular to a surface, right? So what does it mean to be perpendicular to a surface? It means that the angle between any vector in the surface and that normal vector in question should be 90 degrees. Or in other words, the scalar, the dot product should be 0. That's the same thing, okay? If a dot product between two vectors is 0, the angle between the two vectors is 90 degrees, or they're perpendicular to each other. So what this says here is that a normal is the dot product, in German Skalarprodukt, between any vector on the surface and the normal has to be 0, then it's a normal. Okay, so let's just write this down. And since it's more convenient, I just want to rewrite this as a vector product, and that's easy to see. Like what's the dot product? It's really the first component of the first vector times the first component of the second vector plus the second component of the first one, second component of the second one, plus third component of the first one, third component of the second one, and then we get a scalar out since we add them all together. This happens to be exactly the same as when I just transpose one of the two vectors and multiply them and pretend one is a vector and one is a matrix, okay? So we get the exact same result, except that technically the outcome is a matrix with just one entry, 0, but I'll ignore this technicality here. Okay, so, and this is just rewriting the dot product, okay? So now, now that we settled with that one, let's say if I take my position, okay, so t is any vector inside my surface, and I transform this somehow. Okay, so I mean, remember what we want to do? We want to transform the object and we want to transform the normals along with that one. So what I want is I transform the object, that's TO, meaning I transform every vector on the surface of the object, and I want to find a new transformation for the normal, so Tn, that when I transform the normals with that one, that this still holds. So in other words, I want that normal to stay perpendicular to that new surface vector. Okay, and the question is, how are TO and Tn related? And what I've just shown you visually is that TO cannot be equal to Tn. So they have to be different, because otherwise, if I just transform the normal, just like the surface, they should stay perpendicular. So apparently that's not the case. So how do we have to choose them? And what I basically just want to do is I want to just fiddle around with this equation here a little bit and solve it for Tn, which shouldn't be hard because I know n, right? I know t and I know TO, and I know 0. So I basically just need to solve this for Tn. So that's pretty much it. Okay, so how do we do this? Well, I first rewrite this dot product as stated at the top as this matrix product with a transpose. Okay, so and then I solve the transpose. So what is two things? A multiplied transpose is basically each one transposed separately and the order rotated. So that's just how a transpose can be pulled into a product. Okay, so basically this here is the same as that one. So I now got NT N transpose times Tn transpose times TO transpose times T also has to remain 0. Okay, so let's look at this here for a second. What does this mean? It means that, well, Tn transpose times TO shouldn't do anything. Well, why is that the case? Because, well, look at these two equations here. They're almost the same, except that I've thrown some stuff in between. Okay, so I've got here NT, N transpose, times T equals 0. And here I got N transpose times some stuff times T equals 0. So if that goes away, right, I get the exact same equation. So I somehow need to make sure that that goes away. What does go away mean? It means that it should be a unit transformation. It should be the identity. And now you see why identities are important. Okay, so I want that Tn transpose times TO. I want that to be equal to the identity matrix, which are just 1 0 0 0 1 0 0 0 1 written into one matrix, right? That's just identity. Okay, so if I figured out how to make that thing identity, that product, then I figured out what Tn should be. Okay, so now all I need to do is solve that for Tn. So, okay, how do we do this? We bring TO to the other side, so we divide both sides by TO. We can't divide by a matrix, but we can multiply by the inverse. If I multiply by the inverse, I get the inverse here, and it vanishes on the other side. So I now have Tn transpose equals the identity times TO minus 1. And that's okay, let's just drop the identity here. That's silly, right? To say identity times matrix, I can just drop that, right? I mean, this is 1 times something, so I can just write something. So we see Tn transpose equals TO inverse. And now I just need to get rid of the transpose, which is pretty simple, just transpose both sides. So, to make a long story short, how do I need to transform the normals, given that I transform the surface? I need to transform the normals by the inverse transpose of the original transformation. That's it. So you see, Tn is different or potentially different. Now let's look at implications of this reality. So for instance, what happens if TO was a rotation? I just rotated my object. Then Tn is the inverse transpose of the rotation. Now what do we know about the rotation's inverse? We know that the inverse of a rotation happens to be its transpose. So if my original transformation was just a rotation, here it says the normal transformation is the transpose transpose. The transpose transpose is just the normal, the matrix itself. So in the special case that your whole transformation just happened to be a translation, you actually get away with using TO to transform your normals. And that is exactly one of the reasons why a lot of people get it wrong, because they test it and then they rotate the object a little bit and then they see, oh, it looks good. Normals are fine, so everything must be cool. It's even worse than that. Now let's look at another type of transformation, translations. For translation, the inverse transpose isn't equal to the to the original transformation, but vectors aren't transformed by a translation, right? Remember, a vector has a 0 in its fourth coordinate. So when you transform vectors by the means of a translation, then TO doesn't do anything to the vectors. So again, if you use TO instead of Tn, you won't see a difference. So that said, again, if you debug your code and you make this mistake that you use TO also as your translation for normals, you rotate your object, you shift your object around, and it works fine. So you decide, well, it must be good. Now, it gets even worse than that. If you use a uniform scaling, so you scale all axes just the same, and you apply the wrong transformation. So what happens? Well, if you apply the wrong transformation, so TO to your vectors, right? You should have applied the inverse transpose, right? You don't. we translate them by TO. What happens is, well, first of all, the transpose doesn't do anything to a scaling, right? Scaling is just on a diagonal, so transpose doesn't do anything. So you should have applied the inverse to it. Unfortunately, for normals, after you transform them, you always have to renormalize them. You have to, because a lot of transformations change the length of vectors, and you always want them to have length 1. So you always have to, at the end of the transformation pipeline, you generally rescale your vectors to length 1. Now, if you transform them with TO, you make them too long, right? You shouldn't have scaled them, but since you renormalize them, you don't see a difference. If you transform them with a TN, you've made them smaller, right? The inverse basically scales them down, and you renormalize them. So bottom line is you still get the same result. So what does this say? It says that if you test your code with scaling, it'll work fine. If you test it with translation, it'll work fine. If you test it with rotation, it'll work fine. Okay? So do you ever see the bug? No. Now you could say, well, okay, what is left? Maybe shearing. But who shears their thing? So what's all this fuss about? As long as I don't shear, this works, right? No. It already breaks if you do a combination. If you do rotation and translation. Or if you do a non-uniform scale, which you often actually end up doing, then it'll break. So, and that's actually a very long argumentation here of why visual debugging is often doomed if you don't know the theoretical basis. Okay, so still, I mean, even if you know the theoretical basics, you might still end up having a lot of bugs in your code. I mean, I can tell from my own experience that I guess I know the theory pretty well, but I tend to have tons of bugs in my code when I start to write it, right? So, and yes, I do visual debugging, but here's the thing. I know what things to check. I know what things to look for, and that's the big difference, right? Of course, you do some sort of visual debugging, but if I, for instance, check a transformation, I do a non-uniform shearing, right? I check what happens if I squish this. Okay, does it then still look okay? And yeah, yes, in a lot of scenarios, you would see that this breaks engines, this breaks code, and that's in later stages of your development. That is impossible to find. It's a really hard task to find those bugs, right? If you checked all of your code separately, and then now suddenly some designer starts rescaling things non-uniformly, and suddenly your whole lighting breaks, right? Remember, we need the normals for lighting. Your whole lighting completely breaks. You get wrong lighting, and you're like, and then you're looking for what has this designer done wrong, whereas your arrow was made at the beginning. So don't trust code on Stack Overflow, in particular when it comes to, or don't blindly trust it when it comes to computer graphics. So here's kind of everything on one picture. So if we have vertices, we transform them with the matrices right away, and we generally transform them with a thing called model view and model and view, and later on projection. And when we take the normals, we transform them by the inverse transpose of just the model, and we don't apply this awkward P matrix. And we'll later on, so P is just position. Your position times model view, and here's normal times inverse transpose of this model. And model is made up of, M is made up of a model and a view projection, and we call this altogether a model view. Now, what is it with this model and this view thing? Why is there two matrices? Why are they multiplied together? Isn't this just one transformation? Well, in the end, it's one transformation called model view, but where do these things come into play? And we'll see that in the context of rasterization, which will be the topic of the next stream. I'll tell you why I suddenly talk about different matrices and then end up multiplying them still together. And this is easiest seen if we look at how rasterization works, how a GPU works, how GPU rendering works, as opposed to ray tracing. You also have transformation in ray tracing, right? You still want to rotate things, you still want to scale things, you still want to translate things in ray tracing. So a lot of these things just are the exact same process in ray tracing. But in rasterization, they're even more fundamental. So this is why I kind of explain rasterization, and along with that, I'll explain what this view and model and what the projection matrix is all about. And then you will see that the same view and model projection also applies to ray tracing. Not the projection necessarily, but the others also apply to ray tracing. Okay. So that's it. That's it for today's stream. And the next stream, so either next week or if you watch this video on demand, just continue to the next stream, will be on rasterization, and will be a lot more about those transformations and how we use them. We've got a few more minutes, and I would like those few more minutes to take questions. So if you have any questions, let me just go back here. Go ahead. So what have we got? Best terrain technique. Okay, I should have probably said any question regarding the topic, but since there aren't any questions regarding the topic, I might as well answer something that is completely off topic. So best terrain technique, that's way too general as a question to answer it. So are you interested in a or let's just answer all kind of facets of that question, because the answers will be pretty not cool, I guess. So first of all, there's two things about terrain. Do you want to generate a terrain, or do you want to render a terrain? Okay, those two things are separate but sort of intertwined a little bit. Okay, so so when you say best terrain techniques, we need to know, do you want to again generate that or render it? Let's try to answer both questions separately. So if you want to generate, or if you want to get a terrain, so there's again two things. So either you can scan it, like literally, either buy a plane, rent a plane, or render a pilot along with that, and then scan the surface. What most people don't know is that height fields that you get are not, at least when it comes to Earth height fields, are not scanned from satellites. They're often scanned from planes. And you can imagine those planes working like a hand scanner from the 90s, right? Where you just kind of scan, you fly over the surface, and then you scan. Okay, so that's one way to acquire terrain. And the result is simply a two-dimensional grid, right? It's a texture, it's a 2D texture, right? Whereas each point in the grid has a height value. So I'm not going to talk about the details of how this acquisition process works here, because that would alone take hours. But to make, again, this long story short, you can get this input. Okay, so the other alternative is, if maybe renting a pilot and a plane is a little bit too expensive for you, or you want to render a foreign planet, which makes this even harder. I mean, we can fly to Mars, and we've got tons of satellites orbiting, or no, it's not tons, it's to be precise. There's two that are dedicated to this purpose. There's a bunch of satellites, that put like this, that orbit Mars, and they have very sophisticated equipment, so we don't need those low altitude planes, but we can still scan Mars's surface. So anything beyond Mars is pretty much out of reach at present. Okay, so if you want to generate another planet, scanning is out of the question, even if you have tons of money. So what else can you do? You can synthesize terrains, and there's a lot of approaches to synthesize terrains, and in detail they can be a little bit tricky. So I talk about this in advanced image synthesis a little bit, and that is available as a video on demand from YouTube. So you can just go to my YouTube channel and you can watch the terrain synthesis part. I talk a lot about rescale and add, and using Perlin noise, or using noise in general, as a stochastic fractal to generate a terrain. Okay, and that to get it really to look nice, there's a ton of details that you need to observe. There's a ton of knobs that you can fiddle around with to get a nice terrain. By the way, while I'm talking about terrains, if you have any more lecture-related questions, go ahead, and I'll also gladly answer those. But as long as there's no such question, I'll stick with that one. Okay, so that's about the terrain synthesis. So either you use usually a stochastic fractal approach to that one, and I also have a stream in my late night coding session where I implement such a stochastic fractal. So if you're more interested in the implementation details, again, I actually implemented that. And you can see how I kind of fiddle around with that and try to fix bugs and so on and so forth. So, so that's terrain synthesis. Now, terrain rendering, that's the other thing. And that question is even harder to answer. It depends on your underlying, it depends a lot on your underlying data, right? If you have scanned data, it's just there. If you have synthesized data, you might want to synthesize it on the fly, and that again impacts your rendering technique. Okay, so to quickly answer that, because we got another question here, to quickly answer that, so as far as our own research is concerned, we decided to go through a hybrid approach and combine both ray tracing and rasterization to get the best speed. And as far as I know, we're still the fastest in the world to render terrains. And you can go to my webpage to see the joint work with the Technical University of Munich and and myself, what we've done here. So if you just go to hpc.uni-doe.de, so simply High Performance Group at University of Duisburg-Essen, go into publications, you'll find the papers on terrain rendering. But be warned, it's a big engineering thing, so it's not easy to implement. Okay, so we got another question. Is homogeneous coordinates in 3D the only way to answer rotation? Okay, so no. Certainly the answer is no. So there are a bunch of issues in your question. So first of all, I'm not quite sure if I understand it correctly. So but even if I change it and say, are homogeneous coordinates in 3D the only way to perform rotation? So I guess that is your question. Then the answer is still no. So let me change your question once more and now change the actual content and say, did you want to ask, are homogeneous coordinates 3D the only way to perform translation? Is that your question? So if yes, then the answer is yes, at least if you want to stick with this idea of a matrix vector multiplication. Of course, you can also achieve a translation by an addition, right? You can just say, well, if I've got my object here, right, it's got coordinates, and I multiply with a 3x3 matrix and simply add the vector, right? I mean, I simply say m plus input, m times p plus t, right? If I change my whole pipeline, then plus t is not linear anymore, but it'll of course shift the vector by t. Right? The disadvantage of that approach is that you end up with your plus t in between. So sometimes you want to translate, rotate, translate again, right? If you do that, you would end up with a multiplication and addition, and then again a multiplication. And you can't fold those together. Okay, so you would literally have to do multiplication, addition, multiplication. However, if everything is a matrix multiplication, then you can do matrix 1 times matrix 2 and multiply the two together and then end up with one matrix. So in the end, regardless how complicated your transformation is, it'll always just be a single matrix multiplication. Okay, and that's very beneficial. So the answer to your question, if I changed it correctly, and let me know if I did it wrong. If I change your question correctly to this question, are homogeneous coordinates the only way to achieve translation? Then the answer is no, it's not, but is the most convenient and most efficient way. Okay. So okay. So any other questions? Okay, that doesn't seem to be the case. If you've heard that question, there's still the exercise to go along with the lectures. Just as a side note, we currently seem to have some trouble with our Jitsi server, so I updated this over the weekend, and it seems like the Jitsi maintainers made a mistake, and they've pushed their unstable branch into the stable branch, basically breaking everything, and I need to undo that update to get it back to work. So if you're attending, if you want to attend the exercise, right now Jitsi isn't working, but right after the lecture I'll try to fix that. And also in case there's some student here that attend Grundlegende Programmiertechnik, the same server, so the same situation applies. So we're working on that, whereas means I am currently working on that when I'm not giving lectures, and I hope I'll find the point where the Jitsi package maintainers made that mistake, and I can revert to the previous version and we get Jitsi back to work. Okay, with that, that's it for this stream. Again, I'll continue next week, next Monday, with rasterization and more on transformations as well. Then, until then, bye-bye, have a nice week, and stay healthy.